So that can be achieved by rolling I of n by 1. Okay, so roll I think is a Python thing. MATLAB is what is it called? Shift, not shift dimension. Okay, what is the MATLAB requirement for roll? Let's see. Okay, shift arrays, circ shift. Okay, all right. So circ shift I of n by 1 gets me, well, it shifts towards the it shifts down as opposed to shift up. So if I want to shift up, I will just shift it by -1. All right. So see, the ones here is exactly where I want to fill the other item, right? It always appears 1 to the right, and then when I need to wrap over, it's wrapped over here. Okay, so if I want to multiply that by 1 over delta x, I just divided that by delta x, and I get what I want. Now, the final matrix I want to construct is what I'll copy here, plus what I have constructed earlier. Now, this is exactly the matrix I want. All right, so I'll just say A is equal to that matrix. Now it's time to look at its eigenvalues. All right, so I'm going to plot, let's close all the existing plots. I'm going to plot Eig of A with circles. Let me do axis equal grid. Okay, so here are the eigenvalues of my matrix. What do you see here? So first of all, it has as many eigenvalues as the dimension of the matrix, right? That's for sure. So basically, it has 10 eigenvalues, and it lies in a circle. See? Pretty much lies in a circle. What's the radius of the circle? It's 10, right? It's roughly 1 over delta x. Okay, and it is centered at -10 and 0. By the way, when I plot an array of complex numbers, I'm plotting the complex plane. So the x-axis is the real component of the eigenvalues, and the y-axis is the imaginary component of the eigenvalues. All right, so let's just try some other n's. Okay, so we have tried n equal to 10. Let's try n equal to 100. And delta x, let's do this again, and a would be equal to that again. So now I'm not going to actually print it out because it's a 100 by 100 matrix. And now let's plot this as little squares. Right? That's the eigenvalues of my bigger matrix. So what do you see that's different here? Well, okay. What's different is that what's the same here is still a circle, right? Still lies in a circle. And now it's a 100 by 100 matrix. We should have if there are no duplicate eigenvalues, then we should expect 100 eigenvalues. And it looks like there are 100, right? And then the center, it's a circle with radius 100, right? 1 over delta x. And centered at -100 and 0, which makes the circle exactly tangential to the imaginary axis. All right, and just to make sure, like you get, we are confirmed with what we have. Let's just do 1,000. I'm gonna dx a and plot the eigenvalues. Now I'm just gonna plot with dots. All right, so now it's hard to distinguish these 1,000 dots, right? It kind of forms almost a continuous line. And the center, the radius is 1,000, and the center is -1,000 and 0. All right, so these are the eigenvalues of my matrix after my discretization. How does that connect to the eigenvalues of the differential equation? Now let's look at my differential equation. We have called this matrix A, right? Essentially, the spatial derivative is equal to A times U, right? So basically, this is now approximated by A times U. And now if I write down on the next page, I have the D of U1 up to UN dt. So this is a vector of the derivative plus my wave speed, basically the speed of how the wave is going. If A is positive, it goes towards the right. A negative, A goes towards the left. Times my big A times the same array is equal to 0. Agreed? Right? My A is exactly the A I had. So basically dt of, let me just call this my U vector. I'm just have this arrow on the top to represent basically saying U is a vector of n components. It's going to be equal to minus A times A, right, times my U vector. Now, is there any surprise that when A is positive, my scheme doesn't work? Okay. When A is positive, and this minus A times A is going to be doing what? Okay, it's going to flip over the eigenvalues to the right-hand side of the complex plane. Right? So this is the eigenvalues of the matrix A. And if you remember some basic linear algebra, then you know that eigenvalue is actually a linear operator. Right? If you scale the matrix by minus A, then the eigenvalues are going to be scaled by minus A. So eigenvalues of a matrix itself is satisfy this linearity. I mean, well, it doesn't satisfy the other. I mean, it doesn't satisfy that if you add two matrices, the eigenvalues are going to be the sum of the two eigenvalues. But it satisfies our first property, right? I mean, I shouldn't say it's linear, but it scales with the matrix.